as some of you guys may know, in the United States right now, there was a group who believed that, doomsday or whatever would come last Saturday, and some people would be, raptured up to heaven, and others would stay on earth and suffer for the rest of their lives. I'm thinking that those prophecies might have been just slightly misinterpreted, and the event that they were referring to was this wonderful speech toolkit. And the heaven is actually the, enormous pleasure of using it. So I think that, if anything, underestimates the significance of this toolkit. Okay. So firstly, just about the name. It's some kind of coffee reference, hence the little coffee bean with headphones. But this is just whatever name we thought up. So the structure of this whole presentation is, first I'm going to talk for about 15 or 20 minutes, just giving you an overview kind of from all sides of this toolkit. And then we're going to allow people to escape in case they don't want to know more details, and they'll have a short break. And then Arnab and Andre are going to talk about some more code level stuff. Like Arnab is going to talk about some of the acoustic modeling code, and Andre will talk about the matrix library, which is kind of independently useful apart from the speech aspect. And then after that, I'm going to go through some example scripts that we have and try to give people more of a, give people a sense of how to use the toolkit. Now, let's see what the next slide is. So, some important aspects of the project is it's licensed under Apache v2.0, which is a BSD style license that basically allows you to do anything you want with it. There is only an acknowledgement clause which says you have to acknowledge that the code came from there. But it's one of the most open of the standard licenses. The project is currently hosted on SourceForge, which is a standard place for these kinds of open source projects. Some toolkits are very closely associated with a particular institution. Our intention is for it to be more of a kind of something that lives in the cloud somewhere or on SourceForge. I shouldn't have used that word. That's just gratuitous. But the idea is for it not to just be, the pet project of some particular little group, but to represent the best of what's out there. And we welcome new participants. As long as you can contribute code under this license, then that's great. It's basically a C++ toolkit. The code compiles on native Windows and the common Unix platforms. We're not claiming that it compiles on Sun or, other weird platforms, but it compiles on the normal ones. It has some documentation, not as much as HDK. And we have example scripts. These example scripts are not, they're just for resource management and Wall Street Journal, but we're going to have more soon. They basically run from LDC disks. So once you have the disk, you can kind of point them to the disk and just get an idea of how it works. So, oh no, I now realize that we didn't book a large enough run. I think we just advertised this thing too aggressively. It's these Bruno guys. Okay, so I'm going to go through the kind of things it supports. This is just the current features, obviously. We're intending to add a lot more. So you can build a standard context-dependent LVCSR system, with tree clustering. It's been written in such a way that it supports arbitrary context sizes, so you can go to QuinPhone or whatever, and it will work without pain. The training and decoding are both FST-based, and our code compiles against OpenFST. For those of you who don't know, OpenFST is kind of like the AT&T tools, except it's open source. It's a project by Google and some other people. We currently only have maximum likelihood training because we haven't yet done lattice generation, but our timeline for adding discriminative training and lattice generation is kind of this summer/late summer. We support all kinds of linear and affine transforms you can imagine. although not all of these necessarily involve, the tree versions where you have multiple regression classes. That's just because we're trying to avoid very complicated frameworks that would make the tools difficult to use. So a lot of these just support a single transform. All of these things also have example scripts. So it's not just something that's in the code that we know works. It's something that you can also get to work. So I'm trying to emphasize the advantages versus other toolkits. And there's a little disclaimer here that we're not claiming that all other toolkits don't have any of these advantages too. But we're aiming for clean code and modular design. And by modular, we probably mean something a little bit stronger than you would normally imagine. It's written in such a way that it's not only easy to combine the various things that are in there, but it's easy to kind of extend arbitrarily. And we avoid the kind of code where when you add something, a bunch of other bits of code have to know about what you added, and then you have to modify all kinds of, all kinds of other things. The Apache is a big advantage. I know not a lot of toolkits have such a completely free license. And although we don't really anticipate this being used for commercial purposes, our understanding is that a lot of research groups, as a matter of principle, they won't use stuff that has no commercial license because they say, is this research considered commercial by the, people who wrote the license? Will we be sued, etc.? Has example scripts which we're extending documentation. And this whole community building thing, the people involved in Kaldi is currently, it's a group of people mostly involved who met at a previous JHU workshop. It's myself, Arnab, a bunch of guys from BUT, and a few others, including Nagendra Goel. But we're open to new participants. And what we're hoping for mainly is not just people who contribute a line or two of code, but for people who really want to understand the whole thing and can contribute a significant amount. The toolkit is especially good for stuff that involves a lot of linear algebra. It has a very good matrix library that Andre is going to talk about. So if you want to do stuff that involves a lot of matrix and vector manipulations, it's quite easy to do. Also, of course, we compile against the OpenFST library, so you can do FST stuff, at the code level. It's built in a scalable way. Well, it doesn't explicitly interact with any parallelization environment. It doesn't interact with MapReduce or MPI or anything, because we felt that would just lock it into particular kinds of systems. So, but it's been written in such a way that it should still work efficiently when everything is very large scale and you have a lot of data. Our intention is to implement all of the state-of-the-art methods for LVCSR, things like discriminative training, lattice generation, all of the standard adaptation methods. But I think I say on the next slide, something that we're not kind of doing in the immediate future is things like online decoding, which what I mean by that is where the data is coming in, say, from a microphone or a telephone, and it's some kind of interactive application. Of course, you could use it to do that, and building a decoder isn't that hard in this framework. But our basic target audience is speech recognition researchers who want to work on the speech reco, rather than those who. Oh, hello, Mark. I was wondering what everyone was looking at. Mark Gales has entered the room and disrupted the talk by his very presence. Okay. So, some people lately have, it's become popular recently to do a kind of Python wrapper for C++ code. The idea being that you can more easily write new scripts. However, we've avoided that approach partly because it's a hassle to do the wrapping. and nobody ever understands how Swig works. And partly because it just forces people to learn a new language. And probably those who just went to college think that everyone knows Python, but I don't think everyone really does. So we support the kind of flexibility and configurability of that in different ways. Partly, I think it'll become clear later. So perhaps we'll leave till later those aspects. So we don't have forward-backward training. There are no immediate plans to do it. I know I think some people like forward-backward for kind of religious reasons almost, but I don't believe anyone's demonstrated that Viterbi is worse. And it's just so convenient to use Viterbi for, because you can write the alignments to disk compactly, and then, go on.
Dan, have you got that for adaptation as well, where there has been shown to be differences?
Really?
Yeah.
Okay.
It's quantitative data.
Really interesting. But even not lattices, like just a single hypothesis, it makes a difference. That's interesting. Okay. So we'll have to think about that. I mean, it's not like it's really hard to do, but it just wasn't something that we had planned to do. Go on.
So what level, when you do a Viterbi alignment, that's
Mm-hmm.
actually at what level?
Oh, okay. Well, it's at the state level, but it's not really by state I mean PDF index, but it's actually a little bit more precise than that, because if you just write out the state sequence, it's fine for model training, but then if you want to work out the phone sequence, depending how your tree works, it might not be implied by the state sequence. So then we have these identifiers that also contain the phone and transition information. So it's an integer, a list of integers, but those integers are not quite the states. They're something that can be mapped to the states and also to the phone. So I'm just going to describe how this came to be. We had this workshop in 2009. A lot of our focus was on SGMMs. The software we were using there, some guys from Brno University of Technology, including Andra Lukács and others, they built this infrastructure for training SGMMs. It was written in C++, but it relied on a HTK system. And they also built an FST-based decoding so that we could decode in our own C++ code with access to the matrix library. So we're kind of calling that proto-Kaldi. And we wanted to release that recipe, in some kind of open source way, but we realized that the recipe was just too hard to encapsulate because it had HTK, it had our stuff, there was a lot of scripts. So we wanted to create something that could support this stuff and was easy to encapsulate. So we wrote an entirely new, the next summer we wrote an entirely new toolkit that, we wanted everything to be clean and unified and to have a nice new shiny C++ speech recognizer. I think that's this slide. So last summer of 2010, we had another workshop in Brno where we did a lot of coding. And the vision at that time, which I now realize was very unrealistic, was that we'd have a complete working system with example scripts, at the end of the summer. But that kind of didn't really materialize. We had a lot of pieces, but we didn't really have a complete working system. So after I kind of felt obligated to, finish the system, and we had help from others, especially Arnab, in doing a lot of coding after that time. So let me go to the next slide. It's only been officially released something like last week. That's when we actually got all the legal approvals and put it up on SourceForge. This is just a list of the people. I don't think I'm going to go through all the names. This is a list of all the people who have written code specifically for Kaldi. This is a list of people who have done various other things for us or helped us in various ways. And I would describe exactly how for each one, but I'm kind of scared that I've left someone off one of these lists. And I'll just let you read it. A lot of these people have some connection to Brno University of Technology. or people that they know, or things like that. So this is a rather messy diagram. I just wanted to give you some idea of what the dependency structure of Kaldi was, but I decided to put size information into here. So the area of these rectangles is roughly proportional to how many lines of code there are. So these things are things that we compile against. So OpenFST is a C++ library. Atlas/CLAPAC refers to the math libraries that we compile against. And the rough dependency structures, things on top of things depend on them, but it's very approximate. So, for instance, here's various FST algorithms that we've extended OpenFST with. Stuff relating to tree clustering for decision trees. Stuff relating to HMM topology, decoders, language modeling things. This is a small box because really all it does is compile an ARPA into an FST and write it out. Util. This is mostly I/O stuff. There's various frameworks for I/O that will be explained later on, kind of after a break, so we can allow people to escape. This is the matrix library. So a lot of this is just wrappers for stuff that's here. But I don't know if any of you are familiar with CLAPAC and BLAS and those things. But there are C libraries that, for a C++ programmer, are slightly painful to work with because they have all of these arguments like the rows, the columns, the stride. Anything you want to do is this very long line of code. And so there's no notion of like a matrix as an object. So this kind of adds that abstraction, and it is significantly easier to use than this natively. This is feature preprocessing, and going from a WAV file to MFCCs, etc. Gaussian mixture models, diagonal and full. Subspace Gaussian mixture models. This is part of the reason why this toolkit exists. Linear transforms, things like FMLR, MLLR, STC, HLDA, things of that nature. VTLN is in here too, kind of a linear form of VTLN. All of these things up here, these are kind of directories that contain command line programs. It tells you a bit about the structure of the toolkit, which is that we have literally more than 100 command line programs, and each one does a fairly specific thing. We wanted to avoid this phenomenon where you have a program that kind of allegedly does one thing, but really it's controlled by about 1 million options and has rather complicated behavior depending which options you give it. So this is part of the mechanism that we use to ensure that everything's configurable and easy to understand. There's no Python layer, but there's a lot of programs with simple functions. And on top of this is shell scripts. So to do an actual system building, a recipe, what our example scripts currently do is it's a bash script, and it has a bunch of variables in bash to keep track of the iteration and stuff. And it runs the jobs by invoking them from the command line. Of course, there are different ways you could do this. If you love Perl or Python or whatever, you could just do it in Python. But that's how our scripts work. And something that I really haven't included on this diagram, but it is kind of part of the dependency structure, is there's some tools that we rely on. So for language modeling, by default, we use IRSTLM just because of license issues, but probably you'd want to use SRILM if you want to do a lot of language modeling stuff. Things like SPH2Pipe to interpret data from the LDC, and so on. So there's a few. We actually have a kind of an installation script that will automatically obtain those things, just so the scripts can run without you having to manually install stuff on your systems. So I'm just going to briefly summarize the matrix library. Andre will be talking more about it later, but the plan was to allow people to escape after this initial segment in case they're not that devoted that they want to hear about this stuff. But as I said, it's a C++ wrapper for BLAS and CLAPAC. And I should say Andre really has gone to a lot of trouble to ensure that it can compile under various different configurations depending what libraries you have for your system. So it can either work from BLAS plus CLAPAC or from Atlas or using Intel's MKL. The reason is that on some systems you might have one but not the other. Atlas is an implementation of BLAST that's kind of optimized to the specific hardware automatically and is generally more efficient. So the code that we've wrapped includes generic matrices like square matrices, also packed symmetric matrices where you have a symmetric matrix but you only store the lower triangle. And it's like this is the order. And packed triangular matrices. There are other formats that BLAST and CLAPACK supports, but these are the ones that we felt were most applicable to speech processing. Like, we don't do a lot of sparse matrix stuff in traditional speech processing. So and our library also includes things like SVD and FFT. FFT isn't supplied by any of those libraries, but we got permission from Rico Malvar at Microsoft to use his code. So he has a good implementation of that. Something about the matrix library is that even if you don't buy into the whole toolkit, if you need a C++ matrix library, it's probably quite good. In fact, it's surprising that there really doesn't seem to be a lot out there that fills this niche. There's Boost, but it's a rather weird library, and I don't think a lot of people would like that. Okay, a few words about OpenFST. So I assume everyone here knows what FSTs are. AT&T had this command line toolkit, but I don't believe they ever released the source. So when some of those guys went to Google, they decided to have one that was fully open source and it's Apache licensed. That's part of the reason we made ours Apache licensed, because we figured that since we use OpenFST, there's no real point in having a different license because it just gives the lawyers more headache. So we went for the same one. So yeah, we compile against it. For instance, the decoder, it doesn't use like a special decoding graph format. It uses the same memory structures that OpenFST uses. And by the way, OpenFST has a lot of templates and stuff, so that there's not just one FST format, there's a lot of them. So if you wanted, you could kind of template your decoder on some fancy format that would be, let's say, compact or dynamically expanded or something like that. But we're not going to go into that in detail today. So we actually implemented various extensions to OpenFST. Some of our recipes are perhaps not totally in the spirit of OpenFST because those guys have a particular recipe that they do. And ours is just a little bit different. Later on, I'm going to explain why. I feel that there are good reasons for it. I don't know if those guys would agree with me. So a few words about I/O. This was a controversial decision among the group to use C++ streams. In the end, we decided to do it partly because OpenFST also does it. Some people, a lot of people prefer C-based I/O, but we do this. We support binary and text mode formats a little bit like HTK, so that each object in the toolkit has a function that will write, and it takes a little argument, binary or text. So it'll just put its data out to the stream in binary or text mode. And each object also has a read function that does the same thing. So this is a standard thing in many toolkits, that you extend file names in various ways. Like this can mean the standard input, standard output. This is just a command, and this is how it knows that it's a command. This is an offset into a file, meaning it will open the file and fseek to that position. This is useful for reasons that will be described later. So this archive format is a quite fundamental part of the way Kaldi works. And I think I'm going to describe this more later in another talk, but the basic concept is you have a collection of objects. Let's imagine that they're matrices. And they're indexed by a string, where the string might be, let's say, an utterance ID. So you want to have some way to access this collection of strings and matrices. And there might be a couple of different ways you could do that. You might want to go sequentially through them as an accumulation of some kind. Or you might want to do random access. So there's a whole framework for doing this. Basically, the reason is so that your most of the Kaldi code doesn't have to worry about things like opening files and error conditions, and there doesn't have to be a lot of logic about that in the command line programs because it's all handled by some generic framework. But apart from this, we've tried to avoid generic frameworks of this kind. The tree building and clustering code. It's based on very generic clustering mechanisms, things like, I guess, cart or mart, whatever they call it. So it doesn't, that internal code doesn't assume a lot about what your tree is like. It's easy to build decision trees in different ways, including like sharing the tree roots and asking questions about the central phone, things like that. It's very scalable to wide contexts, for example, QuinPhone. I know a lot of, it's hard to write code that will scale to QuinPhone because if you have to enumerate all of the contexts, it's hard to go to QuinPhone, but we basically avoid ever enumerating those contexts. As an example of how we make use of this generality, in the Wall Street Journal recipe, we increased the phone set so that in effect we're asking about the phone position and the stress. Of course, I know HDK supports this because I think didn't you have a paper, Mark, recently about doing that? So, if the phone set were much larger than that, probably an approach based on enumeration of contexts would start to fail. You don't think so? No, I mean like if it was 1,000 cubed is big, right? Really? Okay, well, I'll have to okay. Okay, HMM and transition modeling code. So we've tried to have an approach where a piece of code only needs to know the minimum it needs to know. So the HMM and transition modeling code doesn't really have any notion of a PDF. It purely does what it needs to do, and the rest is separate. So this is probably a pretty standard approach. You develop you specify a prototype topology for each phone that says how many states, what the transitions are. And we make the transitions separate depending on the PDF. So that if the PDFs in two states are different, then the transitions out of those two states are separately estimated. This is just the most specifically that you can estimate the transitions without having your decoding graph blow up. It's not really even clear that this matters, but we just felt that we should do the best we could on that. There are mechanisms for turning these HMMs into FSTs because all of the training and decoding is FST based, so you kind of have to have an FST representation of these things. This is something that we touched on earlier. In our FSTs, so what you would normally imagine is that the FSTs has input symbols that are the PDFs, or some symbol that represents the PDFs, and the output symbols are the words. But the problem with that is, let's suppose you want to find out what the phone sequence was. It's all well and good if your phones had separate trees, so that it was clear for each state which phone it belonged to. But what if you had a larger phone set and you wanted to have a shared tree root, and there wasn't one-to-one mappings, or there wasn't the mapping you needed. So we have input labels on the FSTs that encode a bit more information. And this is also useful in training the transitions because sometimes just the PDF labels wouldn't give you quite enough information to train the transitions. There's a couple of different ways to create decoding graphs. For training purposes, you have to create a lot of these things at the same time. And combining the FST algorithms using scripts would be quite inefficient because you have the overhead of process creation. So we call the OpenFST algorithms at the C++ level and combine them together so that you can create your decoding graphs for training. And we typically put them in one of these archives, like basically a big file concatenated together with little keys in it on disk, so that you don't have the I/O of accessing hundreds of little files. Training uses the Viterbi paths through these graphs. For test time, we didn't use this approach of C++ because there's just no point. It's basically scripts, and I'm going to go through one of these scripts later for those who are interested. these scripts that create the decoding graphs, they call some OpenFST tools, but some are our own. And that relates partly to a difference in recipes, which I'll talk more about later after a break. So Arnab is going to talk later about some of the acoustic modeling code. I'm just going to give a brief summary. Our GMM code is very simple. It's not part of some big framework. It kind of behaves like an object that has, the means, the variances. It can evaluate likelihoods for you if you give it the feature. But it doesn't inherit from some generic acoustic model class, and it doesn't kind of know about things like linear transforms. It just sits there. And things like linear transforms, they kind of have to access the model and do what they want to do. The reason for that is that if the GMM knows too much, then whatever you do that's fancy, you have to then change the GMM code, and it's just not a nice situation. So yeah, we have a separate class for GMM stats accumulation and doing the updates. So for a collection of GMMs, like in a HMM-GMM system, we have a class that pretty much behaves similar to a vector of GMMs. So it's a fairly simple thing. There's no notion of name of a state. It's just an integer. And generally, we've avoided having like names for things in the code. Things are generally just integers. Oh, this lowercase vector just refers to the STL vector. But there is an uppercase vector that does something in the matrix library. Well, look, code has never been case insensitive, has it? Code has always been, even on Windows. Okay, we've got quite a lot of linear transform code. LDA, HLDA. Again, I'm sitting on the fence with regard to the naming of this technique. I don't want to offend anyone. Another of these multi-named things. A linear version of VTLM. I mean, we tried regular VTLM, but everyone knows that it's kind of tricky to get it to work. It was actually the linear one that worked better in the end. This is something new that it's a kind of replacement for VTLM that works a little bit better. I'm going to explain what it is at a later date, an MLLR. A lot of this, so when these transforms are global, the way we handle them is it just becomes part of the feature space. So it's just stored as a matrix on disk, and we use a lot of pipes. So the way it actually works is that this matrix is multiplied by the feature as part of a pipe. This might seem like obviously it's a very silly way to do it from a computation point of view, but it just makes the scripts really convenient to do. Yeah, so when I say they're applied in a unified way, what I mean is that the code that estimates any of these transforms, it really outputs just a matrix. So, there's no like FMLR transform object. There's just, well, okay, yeah, there is for the regression tree one. but for the global one, it's just a matrix. I mean, this was a point of contention among us, actually, whether to do it this way. But some of us felt that it was important to keep the simple cases simple and to avoid having a framework for the cases when none was necessary. Okay, decoders. All of the decoders that we currently have use fully expanded FSTs. And when I say fully expanded, I mean it's down to the HMM state level with self-loops represented as actual, FST arcs. I know there's a lot of way to do this, and initially, one of the thoughts we had would be that, we wouldn't have the self-loops, or we might even have little representations of the states. But in the end, it was just so much simpler to do it this way, that this is what we have now. We have 3 decoders, but by decoder we mean a C++ code that does decoding. It's not necessarily the same thing as a command line decoding program. We have 3 decoders on the spectrum, simple to fast. And the reason for this is that once you have a complicated fast decoder, it's almost impossible to debug. So if something goes wrong, you can always just run the simple one, and you can find out if it's a decoder issue. Decoders, we wanted to make it so the decoder doesn't assume too much about what your models are like. So a decoder has no idea of GMMs, HMMs. It doesn't even know about features. all the decoder knows about is give me the likelihood or score or whatever for this frame index and this PDF index. So the interface that the decoder sees, it's almost like a matrix of floats. But obviously it's not represented that way because you want to, you want to have it on demand computed. So yeah, this is the decodable interface. It's an interface that it's a very simple interface that says, give me the likelihood for this, time in this frame, and like how many time frames are there, and how many PDF indexes are there. That's almost all the interface is. But this is the interface that the decoder requires. So the idea is you implement, El Fantastico model, and you, and it doesn't really matter what the interface of that model is. You create a small object that satisfies the decodable interface and knows how to get the likelihoods from your El Fantastico model, and then you instantiate the decoder with that, or you give that to the decoder. So, Jim, I'm wrapping. Okay. Yeah. So our command line decoding programs are very simple. We don't have like multipass or anything. We don't have. We don't allow them to support multiple types of model. An example decoding program is decode with a GMM, with no multiple class adaptation. So it does a simple thing. And then if we want to support, let's say, multi-class FMLR, we have a separate command line program. The idea is that there might be people coming into the project who might want to be able to understand that command line program, and we don't want to make the barrier to entry too high. We'd rather support the overhead of having to maintain 2 parallel decoders and keep it relatively simple to understand any given one. We support the standard types of features, MFCC and PLP. Our features are quite similar to the HDK ones. We've put in a reasonable range of configurability, but I mean, being realistic with respect to how much people are really working on this stuff. I mean, I think most people who are doing research on this would probably be coming up with their own features. So we don't support every possible combination of everything, right? Every possible change. We only read WAV format because our reasoning is you can always just find an external program to convert it and do it as part of a pipe.
Can you read standard formats for features?
Sorry?
You can load standard format of features like HTK files?
Well, we can load HTK and our own format, but we don't. There's no more that we support. Yeah. I mean, our basic concept of how people will use this system is as a complete system, because once you start supporting model, into conversion, it just gets very complicated. But yeah, it does support HTK features as a special case. We typically will write features and other large objects to a single very large file. It relates to this archive format. So the format of the file is a key, a space, then your object, then another key, a space, then an object. And we have efficient mechanisms to read such files. The 2 normal cases are firstly sequential access, where you want to iterate over the things in that archive. And secondly, random access. And there's different ways to do that. One is you can write a separate file that has little pointers into the file. And another is that you can kind of simulate random access even though you're really going sequentially if you know that the keys are sorted. And another way is if the file isn't that big, you can do random access by just having the code go through the whole file and store all the objects in memory. That's not too scalable, but for a lot of types of archives, it really doesn't matter. Oh, yeah, so the feature level processing, like adding deltas, FMLR, typically each one of those is a separate program. So you have like a sequence of programs in a pipe. And again, that's super inefficient, but it's not like it's really consuming more than 10% of your CPU, so you just don't care that much. This has been written with ease of use in mind. Like I said, there's a lot of command line tools. This is an example of a command line, and this backslash is obviously part of the shell. So this is one of our many programs. The PLP would be a separate command line. This is just, an option. These are the 2 command line arguments, and this I'm going to be explaining later on more about what these means. This directs it to write these things to an archive on disk. So key, object, key, object. And then, oh no, this is the input. It's telling it how to read it. And then this is telling it to write an archive and also an SCP file that kind of has little pointers into the archive so that you can efficiently access the features by random access. So yeah, another example of another feature of this is that there's only one option here, and we typically have no more than a few options on any given command line. I mean, a typical program might support less than 10 options. It's not a very config-driven toolkit. It's more driven by how you combine these programs. Oh yeah, something else about this whole archive formalism is that the C++ level code in the individual command line tools really doesn't have to worry too much about I/O. It can just treat the when it gets something like this, there's very short statements in the C++ that will iterate over it and stuff. So it doesn't have to think too much about the error conditions and the like. Oh, yep.
I missed any discussion about network generation. The rest
FST generation.
Yeah, for CLG.
Okay, there's another part of the talk later on.
Okay, so just as a summary, is that hidden or is that something completely separate that is dealt with elsewhere?
Well, for training, there's a command line program that will kind of do the FST generation for you and generate lots of little FSTs, one for each file.
Right, you mentioned that.
Yeah. So for testing, it's a script that calls OpenFST programs and our versions of OpenFST programs. So I'm going to go through that script later on in another part of the talk. This is not, obviously no one will understand this script, but this is just to give people some idea of how we do training. So, this is a bash script. It's doing a loop over the iterations. And this one is estimating MLLT. I suppose this script reveals a bias. I'm sorry, Mark. But that's what we always used to call it at IBM. So if it's one of the iterations that we do MLLT, then so we have on disk some alignments. This is like state-level alignments. It's in an archive format that I mentioned. So this converts them to posteriors just in a very trivial way by saying that each one has a posterior of 1. This takes away this gives a 0 weight to the silence. This would be a variable in bash. Yeah, so this takes away gives the silence a 0 posterior. And this is an accumulation program that this would be the model. This is a subset of the features. It's a bash variable that would be set elsewhere. I think this refers to the standard input. It means it's reading an archive from the standard input, and that's output by this. See, this means it's writing an archive to the standard output. So the output of these programs is passed by pipes. All of the error and logging output goes to the standard error because we've kind of used the standard output for this pipe stuff. So we're just directing the logging output to there. So then this is a separate program that does the MLLT estimation. It takes in, let me see. It's computing some kind of matrix. And then because in MLLT, after you compute the transform, you have to change the means of your model. So we have we like to keep everything separate. So, transforming the means is a separate operation. So we have a separate program for that. And then we have to compose the MLLT transform with the previous one. So this is another little program that does that. So we're setting another bash variable to make the features correspond now to the new MLLT features. So as you can see, this is a variable in bash, and this would be passed as a command line argument to one of the programs. And it's a command involving a pipe that actually involves calling 2 separate Kaldi programs, each with their own arguments. So obviously you can guess from the names of those programs what they're doing. And then, of course, it seems we have feature subs. Oh, yeah, I think we were estimating the MLLT on a subset of features. So this is like the same as this, but it's using less data. So I think I I spoke about these issues before. Oh, yeah, so we have example scripts for resource management and Wall Street Journal, and these run from the LDC distributed disks. Now, we found in the literature some baselines. These numbers, our numbers, are just the basic context-dependent system with, I think, mean normalization. We have, of course, more advanced things, but those, because it's hard to find in the literature the same thing. We've just given you the unadapted one. So it's slightly better than this number, Wolfgang Reichel and someone in 2000. And there's a HTK paper from 94 that has a slightly better number, but this was a gender-dependent system. So I think basically we're doing the same as you'd expect given the same algorithms. I mean, I was hoping, at the outset of this whole project that the results would be better for issues relating to the tree and quinphone and stuff, but, that didn't really give us anything. So it's working. There's no major bugs. Okay, next slide. Just some notes on speed and decoding issues. These are bigram numbers, and of course the baseline were bigram numbers. We can't yet decode with the full trigram language model that's distributed with the Wall Street Journal corpus because the FSTs, they get too large. We have, of course, decoded with prune trigrams, but that's why we're quoting the bigram numbers. So hopefully by the summer there's a couple of things we can do that we're both working on. One is to have a decoder that does some kind of on-the-fly expansion so that we can decode directly with that. And the other is to have lattice generation so we can rescore. The decoding speed is, for these Wall Street Journal numbers, is about twice as fast as real time. And of course, that's on a good machine. So, I mean, this is tuned so that you don't get more than 0.1 degradation from versus wide beams. The Wall Street Journal script takes a few hours on a single machine we parallelize on up to 3 CPUs. This is just in the example script. We didn't want to include things like QSub in the example script because then it wouldn't run on everyone's machine. Of course, it would be faster if you were doing it parallel. Yeah?
When you say it's too large, the
Mm-hmm.
too large to be fast enough, or is it too large to fit in memory?
To fit in memory. Well, about 10 gig. I mean, FST, everyone knows that FST compilation does tend to blow up a bit. It's not like, if you have the size of the model, you can just about compile it. I don't recall. It's the trigram one from Wall Street Journal. I don't recall how many it was, but I don't think that our stuff is any worse than normal FST setups that fully expand the thing. Oh yeah, okay. Resource management. These HTK results are taken from. I think this is basically the HTK RM HTK recipe, but these results are taken from a paper of mine, like in '99 or something, because I just couldn't find it in the README file from RM HTK on all of the test sets. And the average, as you can see, the average is basically the same. So with the same algorithms, we're getting the same result as HTK. Yeah, and the decoding speed on this setup is about 0.1 times real time.
The script for resource management and the Wall Street Journal are given in the...
Yeah, yeah.
So there's a big variation where average 91 and average 89 are just very...
Yeah, the test sets are quite different.
These things are probably better.
Oh, yeah. These are very small test sets. It's a handful of words that are different. This page is mainly just to give you some idea of the kinds of things that are in our example scripts. We have a bunch of different configurations. So this is the standard configuration. Well, this is the standard configuration because this is what was in the HTK baseline. Adding MLLT doesn't really seem to help. Sorry, adding STC doesn't really seem to help. The splicing 9 frames plus LDA, that actually makes it worse. But then when you do STC on top of that, it's actually better than here. And so this was the IBM recipe. So, sorry, this was the IBM recipe. So I guess there must have been some interaction between these two parts of the recipe that somehow made it work. I mean, I don't know if this would generalize to other test sets. We're going to find out. Spliced 9 frames plus HLDA, triple deltas plus HLDA, triple deltas plus LDA plus MLOT. This seems quite good. And an SGMM system. These are all unadapted. Have a separate slide for adapted experiments. This is doing it, unless it's stated otherwise. Oh yeah, okay, so this is per utterance adaptation, and this is per speaker. So this was 4.59 before adaptation, so it really doesn't help if you do it per utterance, and that's because there's too many parameters in FMLR. This is doing the same thing per speaker. It gets a lot better. This exponential transform is, again, I'm not going to describe what it is. It's something VTLN-like, and it gets quite a bit better. This VTLN is a kind of linear version of VTLN, I believe. It does seem to improve quite a lot. And of course, the improvement is more pronounced on the per utterance level because, it's just like a very constrained form of FMLR. So the only point is to do it when you have less data. Splice 9 frames plus LDA plus exponential transform. Adding FMLR. We only did some of these per speaker because it wouldn't help otherwise. As you can see, there's a lot of different combinations. This is SGMM, including the speaker offsets, the N terms, if you remember. And it does help. So I think Rick was saying that this wasn't working for him, but it seems to be working for us. 3.15 goes to, where is it, 2.68. Oh, I must have forgot to fill this line in. This is SGMM plus FMLR, but no speaker vectors. Yeah. Oh, per speaker. Yes. I think I have these numbers, but I think I must have not put it in. I think our best number was like 2.4 or something, or 2.3. So general plug for Kaldi. I believe it's easy to use. I mean, I hope those scripts didn't scare you guys off. There's a few abstractions that once you understand them, everything becomes quite simple. But it kind of does assume that you understand how speech works. Like if you're some undergraduate who just is randomly moving the script, changing configurations and stuff, it's not gonna work. It doesn't auto-magically know that the features you have are not compatible with your model. So you kind of have to know what you're doing from a speech science point of view. But it's quite, it's easy to use at the C++ / software engineering level, I think. It's easy to extend and modify. You can redistribute your changes or give them back to the Kaldi group. We're open to including other people's stuff, so that may give you more citations. So this is, I believe, the end of this first part. So you can get up and have a drink, and after a few minutes, what?
You mentioned documentation.
Yeah, it has documentation. Kaldi.sourceforge.net. Obviously, it's not as good as HTK, and probably, being realistic, it will never be. But what we'll do is we'll cannibalize the effort that HTK has used and point people to the HTK documentation to learn about speech, and say that after you're done, come back to Kaldi. You see? But okay. So we're going to have a short break. We can have a drink and disappear if you're not, that committed to it. And then these guys are going to talk afterwards. So thanks.